Hello, I have been watching some YouTube channels on other hosts for electronics info, and I have noticed a myriad of devices available for testing capacitors as to its value and other parameters such as ESR and internal leakage. It seems that a common failure point for older equipment is capacitors, usually electrolytic but sometimes film, tantalum, and mica, developing an internal leakage fault that either changes the circuit's condition to being non-functional for its designed purpose, or conducting a DC current that may often damage other components in the circuit it's installed in. The testers that measure ESR, or equivalent series resistance, all actually measure a capacitor's impedance to conducting an alternating current at a specific frequency. These values are usually low in a good electrolytic capacitor, as they are designed to pass or conduct and filter AC currents while blocking DC currents and storing it to pass down a circuit while eliminating a ripple from the AC current supplying power to them. Unfortunately, ceramic, foil, mica, and tantalum capacitors have such a high ESR value to them that they cannot be accurately measured, and one that may have a low value would most likely be one with a terribly bad short circuit inside of it, as an ESR meter will measure a DC short at the same value as an AC impedance most times. Hooking up a low value resistance, such as this 10 ohm resistor, to an ESR meter shows this type of measurement device can be used on regular load resistors to measure values, or even troubleshoot very low resistance shorts if you do not have an ohm meter capable of measuring down to a fractional ohm value, as low as your ESR meter. The ESR meter reads the AC resistance, of this resistor at 9.97 ohms. And the digital multimeter reads 10.1 ohms. Where this takes us is that most testing for leakage of any capacitors besides electrolytic capacitors has been done by measuring leakage of a high voltage, usually up to or close to its rated voltage, and then comparing them to its measured values on a chart usually associated with that piece of equipment. Two units that I have acquired are a Sprague T06A and the Sencor LC53, both having a leakage measurement function capable of applying up to over 600 DC volts to a capacitor and measuring how much current is leaking through it. The Sprague also has an interesting setting it calls an insulation tester, which uses only 30 volts of potential on the test circuit, and it can measure values of resistance up to 10 kilomegaohms or 10 gigaohms. Another instrument that has a useful source of capacitor testing in its manual is the Sencor LC53Z meter. It is another device that uses a high voltage to detect leakage on lower value capacitors. It does have information in the user manual for testing capacitors for leakage, and some of the information applies to ceramic, paper, mica, tantalum, and foil capacitors. Most times it states that the anything but electrolytic capacitors will have a very low to no leakage value at all. There's a special note here for ceramics, and then the different values of ceramics, and it's a good source of information for starters. There's also probably more information in some of their newer LC102 and LC103 meters, but it's a worthwhile document to read to gain some more knowledge. But the basics on this video is this warning here: is this instrument to be operated by a technically trained person only who understands that the shock hazard of up to 600 volts applied to the test leads during a capacitor leakage test. Do not hold the capacitor in your hand or touch the test leads or capacitor leads when making the leakage test with 50 volts or more. So by constructing a lower voltage tester to read a high resistance leak in the capacitor, it would add a safety value to those who might want to do a quick test on things without damaging themselves or the equipment involved. One school of thought is the best test circuit is the one that the component is going to be installed in, so measuring its voltage drop across its leads or measuring its current flow by disconnecting one side and connecting an ammeter in line with it, which both choices rely on care to avoid shock to the technician as well as possible damage to the equipment being tested, and is another possibility for gaining an actual measurement in the actual circuit configuration. What piqued my interest for this specific build was a YouTube video made by tomtestkit, his TTT339 new DIY capacitor tester. Tom went through the trouble of finding an old Popular Electronics schematic for creating an AC-powered capacitor tester using a neon lamp and some capacitors and diodes and resistors, which seemed to be a nice circuit for a tester, except it employed some higher voltages that I wanted to stay away from. And further into the video, he created a single transistor circuit based on a 2N3904, which used the base current as a multiplier in the transistor to energize a diode to basically measure a resistance value, which turned out to be a nice tester. But then Tom wanted to go a little further with it also, and he ended up going and creating a Darlington pair 2N3904 based circuit that he breadboarded and demoed in that video, and seemed to work fairly well. And he was nice enough to do all this work and post a schematic and share it with everybody. He has a schematic content and some circuit explanation in there, and his choice of components for resistors. And it worked out fairly well, but I thought that, as sensitive as that was, he claimed it went out to about the 300 megaohm range, that I could possibly do a little better and get a sensitivity comparable to at least one other tester that's been created by a YouTube user. And I like this choice of circuit configuration because it has minimal components and can be done fairly easily without too much work or component purchase. My thoughts were I could experiment even further and add a third transistor into the circuit, which would give the capability of indicating current flow through a component in the excess of the 10 gigaohm range, while safely using less than 9 volts from a standard 9-volt battery. My configuration after some breadboarding changed a few values of components, and I also discovered that by moving the test lead connection point to each transistor's base. Currently I'm connected to the base of Q1, the base of Q2 would be here, and the base of Q3 would be here. I could adjust the point at which the circuit would start to indicate current flow. My transistors of choice were two N3904 NPN transistors in a TO92 package that were sourced from a foreign country supplier purchased from a large online service in a bulk bag of 100. I screened them for a gain with a low-cost tester, and the majority had a measured gain in the 200 to 225 range. measuring with a DVM with a 10 mega ohm of impedance in the DC circuit volts measurement, the voltage between Q1 on PR1 and PR2 test point measures 8.95 volts. Moving the PR1 test lead connection to the base of Q2, the voltage drops to 8.14 volts, and it does give an indication on the lamp. And moving it to Q3 gives an indication of 7.66 volts. So the maximum voltage that would be supplied to a component would be 8.92 volts, but not giving an indication at a 10 mega ohm resistance. Moving it to the base of Q2 does give an indication, but also supplies a lower voltage. And Q3 is also the same. It will give an indication, but even at a lower voltage still. The information for the circuit that I created is on a site called multisim.com. The schematic itself, if you search for it, is called a Gigaohm _cap_leakage _tester_1. In it, I had to change and set some values. One of them was for the LED as an indicator. I set that with a yellow indicator light and a on current of 6 milliamps. And then you can change that by highlighting that component, getting it to where it goes to an edit field. And then the transistors themselves are all set for a gain of 220. You do the same thing, you highlight that component. And you can set what's called the maximum forward beta of 220. And there's only two other things I was changing to check with the circuit. I would change the value of the resistor, which would be the capacitor under test, between the PR1 and PR2 points. Currently I have it set at 455 kiloohms, and that gives an indicator on the LED, and has a current flow of negative 3.6 milliamps. To change that value, you click on the resistance itself out of that resistor, and you can change it either with a slider or a direct keyboard entry in this field. Once you click out of it, it will change the value, and then you need to go up to simulate the circuit again, run it. And at this point, if you notice, the resistance has changed to 700 kiloohms, and the LED itself is barely lit. If I go to the resistance value and go up to 1.3 mega ohms, you notice the the LED is just barely yellow. If I slide it up to 2.4, it basically goes dark. to change connection points on the schematic, you have to stop it, stop the run, highlight your connection point, delete it, come back onto your resistor where you'll get a little spool of wire, click on your connection point, drag it past your voltage setting, your voltmeter, connect it to Q2, click on it again, come off of it, and then click, and you have a connection point now to the base of Q2. What this does is it starts to make conductance on this circuit between the collector of Q2 through the emitter to the base of Q1. So it multiplies the gain of Q2 with the gain of Q1. And at this point, if I start the circuit up, we are only set at a, I believe, a 1.2 or a 1.4 mega ohm resistance. We'll get back to that. To run the circuit again, it's a 2.4 meg, and if you notice, our LED is brightly lit with a current flow of 15 milliamps. What I can do is change that to 24 mega ohms. It's still lit. It still has a 14 milliamp current on the LED. If I go to 240, that drops my current flow through the LED to 1.3 milliamps, and if you notice, the LED itself is almost extinguished. And just going a little bit higher into the 300 range basically extinguishes it. And if you notice here, we will have a voltage potential measured between the leads across the resistor. At this point, it's kind of strange because it gives a positive and negative voltage. But if you add them up, it is not quite 8 volts, but it's under it. It's a little bit different than real world circumstances. And then if we stop the circuit again, we can come up and delete this selection point. Come back to our resistor. Get our spool of wire going, run it by our PR1 test point so that makes connection. Then run it up to the base of Q3. Click on it until it's bright red, then go off of it and click on it. And at this point we are multiplying the gain of Q3 through the collector to the emitter connection from the base to trigger the base of Q2 through the collector to emitter of that transistor to the base of Q1 to multiply the gain of that transistor through the circuit. And running the simulator again, we have a bright indication on the LED at 385 mega ohms. If I jump up by values of 10, at 3.85 gig, we still have an indication. At 38.5 gig, we have a dimly lit indication, but it is still there. And by the time we get to about 50 gigaohms, the current flow through the LED is listed 1.3 milliamps, and it's barely lit. And also, as a note, I did set up an ammeter here, and the current flow through the base of Q3 is negative 144 picoamps. I don't have anything to measure that low. Comparing the online multi-sim simulator to the actual circuit, I will connect to the base of Q3, which gives me a little bit of an indication. And I have a small soldered perf board. I don't know if you can see, but we do have two 10 gig surface mount. I believe those are like 0805s on this side. They're plus or minus 40%, so I don't know exactly the value. I can't measure them. And then on this side, I soldered 4 1 gig surface mounts, and I extended leads to the other side of the board to test. So on the Q3 connection point, just touching the leads is giving me an indication. Giving it dead short is giving more of an indication. 10 gig connection gives a fairly bright indication. What I'm going to do is hook the two 10 gig resistors in series. Right now, if you notice, there's no indication, so there's no complete circuit. And through the two 10 gig resistors in series, we do have the LED lit up fairly well. If we move our connection over to the base of Q2, we have no indication at 10 gig. We also have no indication at 1 gig, and I'm not even sure what my trigger point is at this range on this board. I do have an assortment of other resistors to test with, and I have a string of 10 mega ohm resistors in series on the breadboard. Now these are only 1 mega ohm resistors, I'm sorry. It gives a bright indication at approximately 5 mega ohms. And you also have to remember that this is where handling both boots of the test clips at the same time gives an indication. I did play around with using an ammeter on a DVM to indicate a current flow as to where it might trigger. But in order to just get it to light up to a bright level, I'm coming up to 1 microamp on the ammeter. One possibility for measuring the resistance at what this might trigger at is to try to use an ohmmeter in line with the actual conductance of my body. At this point I am set to 40 mega ohms on this meter. It has an impedance itself for an internal resistance of 10 mega ohms. And by grabbing the probe at one end and the test lead at the other, I can start to get a light indication by gently squeezing with my left hand on the clip, and at what the meter is measuring at 37 mega ohms, you start to get an indication on the LED. Squeezing it harder lights it up brighter and brighter, of course, until you get just about a full value at 2 mega ohms, and of course a dead short is a very bright indication. Measuring my resistor string, gives me 4 mega ohms from that point to that point. And it gives about a full lit indication. So outside of stringing together a large amount of 1 mega ohm resistors, I don't have anything bigger than that available in that range until I go up to 1 gigs. I can't really measure the resistance at which would trigger that light. All I know is it's fairly sensitive. And now to get on to testing some prospective devices. I have an assortment of capacitors. Some are defective, some are good. This one was sourced in bulk. It's a 0.47 at 12 volts. Ceramic. I'll test it at the Q1 connection point. We got a short indication on the meter and the light went out. And if we take it with this connection and move it to the base of Q2, you see there's no current flow at that resistance measuring point, and if we change it to Q3 it's the same. Now what we can do is, since this capacitor is now charged up to at least an 8 volt level, we can change the polarity on it, and the voltage that was stored on the capacitor is fighting against the circuit, but there's such a low current flow going through the capacitor that it can't be charged in order to shut it off. So what I did was change the measurement point back to Q1, and it basically reversed the charge on the capacitor. Moving it to Q2, the capacitor is still holding a charge, so it has no internal leakage. Moving it to Q3, it's still holding a charge, but if you see, it started to leak off, and we are getting current flow at that resistance level. Now, out of curiosity, if we go back to Q2, it gave an indication, but there's enough current flow that's working against whatever actual internal resistance that is in this capacitor, where it's actually charging the capacitor back up again, and the light is going slowly dim. If we go back to the base of Q1 at the higher voltage, the indicator light goes out, and again it's still out at the Q2 connection and at the Q3 base. But there we go again. It's got a little bit of internal leakage, but at that level, we're talking at about an indication level of 40 or 50 mega ohms. You can probably consider this capacitor good. Out of the same batch, I checked a bunch of them in the parts bag, and I found one that is suspect with some issues. Same capacitor from the same batch again. That one did charge up well. At the second Q2 connection position, it's giving us an indication of an internal short. We're going to go back to Q1, and we're going to reverse the polarity on this. And by reversing the polarity, we have a resistive continuity through this capacitor. And the curious part is, if we reverse it back, there's a little bit of noise in the capacitor as well. It does eventually get to the point where the light goes out, the LED goes out, but we have leakage at the Q2 connection in both polarities. Comparing that again to the good capacitor, we will see that it takes an initial charge and the LED slowly goes dim at the Q2 connection. And reversing the polarity is going to cause the same thing. It has to dissipate the charge in the opposite polarity, and now it's taking it down. And if you notice, this one does charge up a little better with the capacitor in this polarity configuration, which is curious considering these are non-polarized. I did do some checks with some electrolytics as well. The 4700 ohm R1 resistor for the PR2 test point is the source of a positive voltage, so we're going to put the negative to the negative on the capacitor. Go to Q1. This is a 440 microfarad at 330 at 35 volts. And I don't know if you saw, but it did conduct current to charge the capacitor and extinguish the LED. If we move it to the Q2 position, it's also testing to have still either start a charge or have no leakage at this point. But if we left this on here long enough, there would probably be enough of a internal drain in the capacitor where the LED would start to come on. But it's going to take a while. I'd consider this capacitor to be good, but it's a brand new part. Her new old stack. I have a what is supposed to be a 50 microfarad 10 volt non-polarized. Anyways, take my word for it. This is slowly taking a charge and dimming the light. But it's misbehaving bad enough where I'm going to check it out with a couple other meters to see if it's actually close to its marked value. It is an old capacitor, probably at least 40 years old. I'll try it on my capacitance meter first. And the meter says we have a 94 microfarad value, which is overachieving by quite a bit, and reversing polarity on it since it is a non-polarized gives us a 94 microfarad reading as well. So now I can try the ESR meter just for giggles. It does come up with a measured value of 0.02 ohms. And at this point the video editor ate my homework, so you'll have to have this audio until the next track comes in. So that's as far as I've gotten with this project. I haven't tried to put it on a perf board in a box yet. It'll be interesting to see what size I can get it on. The only design flaw I might make, instead of making, or design part I might make, instead of putting a switch onto the connections for Q1, Q2, and Q3, I might actually have some breakout pin sockets on the outside of the box to put jumpers to between the transistor and another, wire that to an external point to hook up jacks to, banana jacks, instead of using a switch, because I don't have a lot of confidence that a switch is not going to add some sort of capacitance or resistance to the circuit that might give a false indication at the higher ranges. If I isolate that just by using direct wire connections, I think I can eliminate that. And then there's other things that can be played with this circuit here. There's the resistor that's shunting across the LED. I am currently using a 2.2 kilo ohm value resistor that has a measured resistance of 2.1 kilo ohms to shunt the LED with, and putting my test leads across a 1 mega ohm resistor gives a dim indication on the LED, but removing the resistor from the circuit makes it quite a bit brighter, so you can adjust that value to adjust the sensitivity of the LED indication, and you will probably have different results depending on the gain of your transistors as well. The ones I chose, like I said, they were 213904s that had a gain of somewhere between 220 and 225. So I thank you for tuning in to my YouTube channel and checking out my first video creation, and I hope to see you again in the future. Please feel free to give me a like and subscribe if you enjoyed my content and would like to return in the future for more information. Thank you.